Hello, everyone. Brian Wilson, host of the API Management and Gateways track here, coming to you live, day 3, TechCon. We'll keep rolling today with our next session. And before we start, you've heard this all before, but just in case you haven't, ask us anything. Chat is always open. We want the questions. Please make it interactive. At the end of the session, there will be a poll or survey, bottom left corner of your screen. Please take a moment and answer those questions, provide that feedback so we can continue to improve our TechCon sessions, the TechCon conference in general. We depend on your feedback for that and want to get your insights. So with that, let's get started. Team, over to you.
Perfect. Thanks, Brian. And thanks everyone for joining in this last day of TechCon. Today we're going to talk about some fun stuff, security, everyone's favorite or nightmare. Talking about DataPower security, we're going to go really deep dive and quantum safe encryption, what we are doing to make DataPower quantum safe, basically. But my name is Ulaş Çubuk, by the way. So I'm here to present with my colleagues Prag, Nacha, and Thomas. So they are the best, security experts and engineers to present here with me today. So thanks to them. And my name is Ulaş Çubuk. I'm the product manager for DataPower. So before going deep dive into the security, so just to set the scene, so if anybody in this session now not aware of DataPower, so DataPower Gateway is not just another runtime, right? And it's not just another gateway. So it's basically it's the IBM's enterprise security and application gateway. It sits between various network zones, various applications, clouds, and it sits in between various things. Basically, it just linking them in a controlled, secure, and optimized manner. And by doing so, with its critical protocol bridging and integration capabilities, it also combines, as I said, various workloads from modern event-based workloads to API workloads to B2B workloads with the traditional services. And in that sense, the DataPower is currently used across many industries, across many clients around the world. So there are some figures there, but that's just a ballpark. So I'm sure there is even more than that. And that being said, it's also the runtime gateway of API Connect. So it powers the API Connect. It powers the AI gateway of API Connect, which I'm sure you heard some of them in this TechCon event. So it provides the integration, routing, rate limiting. So all those necessary functionalities of API Connect. So it's the core of API management solution, basically. So that being said, DataPower Gateway, so why it is so unique and critical in the market? So because it addresses a quite large set of use cases. As I said, it can handle traditional SOA workloads, B2B workloads, APIs, AI-based AI, kind of LLM protection with as I said, probably you heard about the AI gateway, right? And by doing so, you can position the DataPower gateway to deploy it into various with various different scenarios. You can most of our customers really using DataPower not only in the DMZ, which is for DataPower's probably the most critical, critical use case to prevent the backend applications, to prevent the enterprise resources, critical sensitive resources from the upcoming traffic. But also most of our customers are using DataPower Gateway from their internal or their own applications when they want to access the other B2B applications or other third-party applications. And more or less, it's also expanding to cloud, right? So DataPower can also be, with its virtual form factor, can be also used as a cloud gateway. So and we see this mix and match pattern quite a lot. So as I said, it can handle various use cases. So in that respect, it's not just one dedicated use case gateway. It's a unified gateway. It's kind of a what we used to say is like a Swiss Army knife. So as I just touched a little bit, DataPower, well, it comes in two flavors, right? We have physical appliance and we have also virtual appliance. With physical appliance, that's from when we talk about security. So that's kind of our favorite one, to be honest, because it comes with the DMZ ready security built into it, right? Optimized for security, optimized for performance, and it protects our customers at the edge of their organization network. Whereas with the virtual, again, we provide that built-in secure dedicated system of, let's say, kind of operating system, right? But you also get the flexibility of deploying DataPower into various places. So it basically gives you the elasticity, right? You can either use with the same offering, you can either use it as a virtual machine on VMware, and meaning that you can deploy this VMware on a VMware hypervisor on cloud or on premise, and you can adjust the scaling based on your capacity requirements. And you can either or you can use it as a Linux application. Just comes as a RPM package, right? And you can deploy it on a Red Hat Linux host. Again, use it on the cloud or wherever you want, as long as it's on Red Hat. And the last, the last one is obviously the containers. So you can. DataPower also comes as a container form factor where you can deploy it on Kubernetes or OpenShift orchestration environments. And by doing so, remember, this gives you, as I said, elasticity. So you can scale our gateway for any environment wherever your apps and data reside, so that you can adjust also the security requirements from more centralized manner to decentralized manner. So this is important because, you know, the security requirements for a single backend application, perhaps a small application, might not be the same as the security requirements when you want to protect all your traffic on the DMZ. So yeah, that being said, what are the key strengths of DataPower? So yeah, this is obviously integration, as I mentioned, can bridge many different protocols, can do message transformation and things like that. So that's also a bread and butter of DataPower and performance. So it is basically DataPower is used over the years to handle mission critical environments. But yeah, today our focus is security. So what maybe the most critical and important components and capability of DataPower. And in terms of the security, so we can talk about, of course, the features DataPower provide as a gateway where you can secure your in-flight traffic, right? So that's with that, DataPower gives you lots of built-in policies that you can apply on your service, on your gateway API. And there are, I'm not going to go through all of this, but so yeah, these built-in policies it's very rich. So you can do the message validation, for example, JSON validation or XML validation. So most importantly, AAA authentication authorization audits. You can do a token translation in a AAA policy. So very, very important. Obviously, you can do filtering. You can do message level protection. So it's not only TLS or transport level security, but with DataPower you can do message level protection. You can encrypt, decrypt, or sign and verify. So all of them are used for dedicated security use cases. And of course, the most important thing to remember here is these policies will be available for not only your classical HTTP API-based traffic, so you can use it in a sense that's where you can protect different protocols, different traffics. And these are the things that DataPower provides out of the box, obviously, to secure your traffic. But apart from that, DataPower is also built itself, it's secure. So that's what I'm trying to say. It's an enterprise-grade security platform. So because enterprise-grade security requires that secure platform. With our built hardware, physical appliance, so you will get all this purpose-built physical security, like it is sealed, tamper-evident case. You can't use a USB port in a, you can't install anything on DataPower. You can't install any, you can't inject any, extra components yourself. It comes with an encrypted flash drive, trusted platform module, all these kind of things. And recently we also announced our FIPS level 3 certification. I mean, the next iteration, we were already FIPS certified, but we just announced our next iteration FIPS level 3 certification. So which comes with our physical appliances with HSM embedded into it. So which is another unique differentiator that we have in our gateway. And the second thing is, so apart from this physical security, of course, so it comes with a security hardened firmware for both physical and virtual appliances, because we call it firmware. When I said we have a special operating system, we call it firmware. It is signed and encrypted by our developers here in this session. And as I said, you can't have any arbitrary software. It's really dedicated just for your gateway requirements, optimized and lockdown configuration. So yeah, with this intro, and okay, one more thing. So recently I want to mention this as well, because this was highly requested feature. So in order to manage our DataPower boxes, so we have built in SSH server components, right? It is probably you're aware of this. This SSH server component is both used for the management access, for CLI access, and in some cases for SFTP scenarios. It's also used underneath. So previously this profile was not giving you the control to choose your host key algorithm. So it was there, obviously, but it was not. So most of our customers wanted to customize or select their own preferred host key algorithms. So we exposed that functionality as I said, highly requested by many of our customers. So thank you for waiting for this. And also we added lots of course, more secure key algorithms like ECDCA and similar SSH host keys. Okay, so that's being said, I want to hand over the speech here to you guys. So we have recently introduced last year in December with our 10.6.2 CD release. We introduced a tech preview for quantum safe algorithms. So that being said, okay, over to you guys. So let me give the stage to you.
Hey, thanks, Ulash. Hey, everyone. My name is Parag Chinchale. I'm the security lead with DataPower development. And with the introduction from Ulash, I kind of wanted to also, continue that announcement of quantum safe, quantum resistant algorithms. Now that, DataPower has introduced them, let's kind of, first understand why that was even needed. Why that move to quantum resistant algorithms. So if you want to go to the next slide, Ulash. Thank you. So, let's first understand what is now called classical cryptography. So what is classical cryptography, and how is RSA and EC elliptic curves implemented? And once we've done that, of course, this is verbalizing and simplifying the mathematics behind it. But it's a very short intro, just to kind of recap our understanding of RSA and EC. And then, once we've discussed that, it will become somewhat evident as to, why we needed to kind of go and implement the quantum safe crypto. So as you're aware, in PKC and public key cryptography, you're using a key pair, an asymmetric key pair. And with that key pair, we can do encryption and decryption. So that way, you can send messages. Alice can send messages to Bob. Bob can send messages to Alice without, eavesdropper being able to decipher the contents of that message. And the way it is done is the mathematical property of the key itself. The key pair is devised such that only the person with the private key is going to be able to decrypt that message. And for RSA, that has to do with the factorization problem. So effectively, what's crucial there is, let's say we start with a prime number, and then finding a co-prime to that, a number such that the GCD is 1, such that if you were to do a multiplicative inverse modulo of that number, what you then derive is the private key. And that relationship is the problem that is difficult to solve or to break. At least with current technology, if you have these two numbers, you cannot go from the public key. You cannot say that, oh, here's my public key, and I know the relationship between the two, so I should be able to derive the private key. That's with the current technology, we can't do that. We don't have the necessary resources to be able to easily do it. And so the hardness problem here, is the factorization problem, and that's how RSA works. So far, we're safe. The largest RSA key that was broken was, I think, 800 some bits, 829 or something like that. So we said, okay, we can move up to 1024-bit key. And, at least that's publicly known, the vulnerability is 829 bits. But even 1024 bits is considered weak these days, so we moved up to 2048-bit. So naturally, we can increase the key size, but then with that, we're also increasing the complexity and the computational requirement, the resource requirement to perform those operations. So in order to kind of simplify that a little, the next thing was elliptic curves. If you want to go to the next slide, Lush. So elliptic curves, they provide a similar set of security. You know, they're about just as secure, or maybe even more secure than RSA, but with a smaller key size. And so, you know, whereas with RSA, you're working with, you know, with the Galois field, you know, here you're working with a finite field. And in this particular scenario, we're working with the discrete logarithmic problem. So effectively, what happens here is that, you know, similar to RSA, you start with a random key, which is your private key, and you find a known point on a curve. You know, so this is a planar curve, the elliptic curve, and you can approximate that curve such that it becomes a set of numbers. So you know, this generator point defines one known point on that curve. But if you were to kind of look at the entire field that is defined by that curve, then that set of numbers is will be numbers that fall on that curve. You know, so within the space of that curve. And so you take this generator point and the private key, the randomly chosen private key, and from that you derive a public key, which is you know, which is sort of the representation of that public key. I mean, effectively, what you have here is again relationship between the private and public key, similar to RSA. You know, these key pairs are mathematically related, but again, you know, it's a discrete logarithmic problem, a problem that, you know, you cannot solve in an inverse fashion, right? So that's what gives it the kind of cryptographic importance that we're seeking. And on the other hand, it's a smaller key. So technically, you know, you're using less resources. And that's not always the case, because now, you know, you may have added some mathematical complexity to the problem. But, you know, it doesn't change the fact that, you know, we're working with smaller keys. So there's more room for increasing key sizes as we go. Elliptic curve, you know, will be typically used with key agreement, or, you know, integer factorization problems, as well as, you know, for digital signatures. So, you know, where exactly is ECC used then in encryption? It's somewhat indirect. You know, you've done key agreement with ECC, you can implement symmetric ciphers, and then, you know, embed derive the key using the key agreement. So what you have now is key agreement done using elliptic curves, and key derivation, and encryption done using symmetric ciphers. So the end-to-end result would be as strong, if not stronger, than, say, you know, with RSA algorithm. So let's look at, if you go to the next slide, Ulash, let's look at, you know, what is the level of security that is offered by RSA, or what makes RSA secure today. As I mentioned earlier, you know, at least the publicly known RSA key that was factored is 829 bits. And, you know, also as discussed previously, the problem, the factorization problem requires computational resources that, you know, we do not, at least, you know, known resources exist that can, you know, that are shown to break standard RSA keys, you know, let's say 2048-bit key. You know, the way that factorization works, it's not going to be easy for us to find those factors. And you know, again, the modulo exponentiation that we're doing with these keys is what makes them stronger. So you know, the entire concept of that key, the way those keys are generated and the way they're related with each other, is the mathematics of it, you know, is what makes it strong. So similarly, if you look at elliptic curves, if you go to the next slide, With elliptic curves, again, you know, the problem you're trying to solve here, you know, if you were trying to derive the keys, the problem you'll be solving is that of discrete logarithms. Again, like factorization, it also poses the same computational limitations. And as we also saw earlier, a standard RSA key today is 2048-bit, whereas a 256-bit elliptic curve will give you, you know, security level that is similar to a 3072-bit key. So elliptic curves, you know, they definitely provide a stronger key. So, so that would, you know, you would think that is what with RSA and ECC we should have the necessary sense of security, and you know, we probably wouldn't need anything more. I mean, I know that there are two types of curves with EC. We have the prime curve and the equivalents, the binary curve. One is derived over prime field, the other is, you know, 2 to the power of n, you know, so it's a binary field. The binary field curves are less popular, not because, you know, they're less secure, but the complexity involved there, you know, that there's maybe more unknown vectors, you know, attack vectors versus the prime field. But that's really isn't the reason why, you know, we're not using elliptic curves, or that's not the reason why, you know, we believe elliptic curves are weak, or, you know, that RSA is weak. It's because of the inherent nature of what quantum computing does, or what it's capable of doing. So if you go to the next slide. So what exactly are quantum computers? And I will hand this over to Thomas, who will kind of walk us through that.
Thanks, Parag. Yeah, so one of the fundamental concepts of quantum computers is superposition. So it's really the concept of being able to do numerous tasks at the same time. And so it can do like concurrent calculations, right? It can maybe, you know, generate a lot of prime factors for a given number. It could do a lot of things in parallel. It's a little tough to grasp. You know, this capability of doing more than, you know, just one thing at once, like classical computers can do. But that's, you know, that's the way quantum computers work. And, you know, this power, this capability, you know, will net many benefits, you know, over time, like weather prediction, drug research, energy research, a bunch of different areas. But this powerful capability also makes a quantum computer ideal for breaking cryptographic codes. And, you know, we may ask, well, why or how? And it really has a lot to do with their massively parallel nature, I guess you could say, or their concurrent nature. And to talk about it a little bit more, Ulash, if you could go to the next slide. You know, we'll cover Shor's algorithm. So this was developed by Peter Shor. He's a mathematician, and he really came up with, or he's known for, 3 algorithms. One is related to factoring, you know, one's related to discrete logarithms, and one is related to period finding. But the term Shor's algorithm typically relates to his algorithm for factoring, for finding prime factors. And basically, once the quantum computing matures, a suitably large and stable quantum computer, you know, should be able to apply this algorithm with like a log n time complexity, which is really unheard of. And that's the reason why some of these algorithms that Parag has already talked about, which, you know, we look at with classical computing, being able to find prime factors as being a inordinately complex time complexity, or inordinately long time complexity, to be able to find the prime factors that are used by these algorithms that he just talked about to do encryption and decryption. It really happens in much less time with Shor's algorithm, right? So you apply a sufficiently capable quantum computer to this problem of trying to get the decryption key, basically, or to the encryption decryption prime factors, then you end up realizing that there are inherent limitations with RSA keys, like finite field Diffie-Hellman and elliptic curve Diffie-Hellman algorithms. So you may ask yourself, well, if it hasn't yet matured enough for this to be a problem today, then why do I need to be concerned? And that leads us to the next slide. So we introduce the Mosca theorem here, and we say that the time that you need for I guess the migration time and the security shelf life, like how long do you need your secrets to be secret, basically, is the Mosca theorem categorizes this as basically X plus Y. And given quantum computing, how much do you anticipate, how much time do you take it will, how much time do you think it'll take to compromise your keys such that the data is accessible? And so that that's Z here, it's the time to compromise. So if X plus Y is greater than Z, if the shelf life of your asset is actually less than the time it takes to compromise this the asset, then you've got a problem. And on the surface, this seems pretty simple, but it's something we need to be thinking about as the field of quantum computing matures. And it seems like we're seeing new developments, improvements in the technology. Almost on a month-to-month basis, you'll see some sort of announcement that some company has gotten an even faster quantum computer, more capable, more stable, right? So this is something that we should be thinking about now, and something that DataPower, the DataPower organization, is thinking about now. So which brings us to the next slide. So quantum safe cryptography is the concept of how do we create an environment, an encryption capability that can sustain the quantum era, right? How do we make it to where when we encrypt something, if a quantum computer of sufficient maturity, power, capability were to be introduced, in the near future, would these assets still be protected? So yeah, exactly. So the next slide shows that it's not just a future problem. It could be somewhat of a today problem, right? We're not trying to fearmonger here, but in a use case like this, where you have a cyber criminal is acquiring assets, their encrypted assets, to be decrypted later. Obviously, if it's like a bank account transaction, maybe it's not as big of a deal because that'll go through before they can get a chance to really do anything nefarious with that transaction. But if there are like trade secrets, maybe there are drug compounds or research, that sort of thing that you want to protect over a longer period of time, then it's really when you anticipate cryptographically relevant quantum computers to become available that this really becomes like a business concern, right? When can a quantum computer be, when can it apply the Shor's algorithm to basically break the keys and access this information? Because it could already be stored like on a competitor's in a competitor's data warehouse, whatever, right? It could be, ready to be decrypted once the technology becomes available. Right. So seeing this on the horizon, the National Institute of Standards and Technology sent out a call for draft proposals in 2016, and the time period has obviously elapsed. It is 2024. You've got the first product with quantum safe cryptography available. And so a lot of thought has gone into this, which Parag will discuss here in a minute. But it's something that that is available today now for a tech preview, and it's ready for customers to use to protect their assets, in the advent that they have, especially for long-term assets that they want to protect the cryptography for. Now I'll turn it back over to you, Parag.
Thanks, Thomas. Okay, so as we saw in the previous slide, the NIST has standardized certain operations and certain algorithms for quantum safe crypto, quantum resistant crypto. And those standards are numbered FIPS 203, 204, and 205. The 203 is what's of immediate interest to us. This is where one of the algorithms that was submitted, the Crystal Kyber, is now called, MLKEM. The ML is the module that's the mathematical foundation of that algorithm. And the KEM is a key encapsulation mechanism. So this algorithm will be used, or FIPS 203 essentially standardizes and defines the algorithms that one can use to make your communications, if you're using TLS, that TLS communication can be made resistant to quantum computers. And the way you do that is using one of these algorithms, using MLKM algorithm. But we can also just quickly touch upon what 204 and 205 defines and brings to us. So similar to MLKM, which is used for encrypting the data in transit, MLDSS, the digital signing, uses similar module lattice, the crystals, but this algorithm was previously called dilithium, and now it's the MLDSS. So this is for signing. So this is your authenticity and non-repudiation clause of cryptography. This is where the MLDSS algorithms would come into picture. And FIPS 205 is, and I think that's a typo there. FIPS 205 is stateless hash-based signatures. So that's yet another algorithm, also intended for digital signing, and also meant for non-repudiation. So that's basically you have two different algorithms for that. And then Falcon, which was an algorithm that was submitted as of when we created these slides, and it still hadn't been standardized. But it is also intended for digital signatures. It uses fast Fourier transformation on a compact lattice. So it creates a smaller signature. It's more in terms of size. It's probably more efficient. But again, all these algorithms, they provide you a medley of encryption and signing. So if you want to go to the next slide, Lush. So exactly what makes an algorithm quantum resistant, or what is a quantum safe algorithm essentially? And this is, oversimplification of the mathematics that is involved. I mean, we're taking some concepts of abstract algebra and, verbalizing them. But, in that simplified view, consider the fact that, when we first looked at RSA and EC, and we talked about factorization problem, we talked about discrete logarithms. In some ways, you could treat that as deterministic, as in if you are given some ciphertext, or if you're given the public key, and the problem you're trying to solve is, well, what are the factors, what are the prime factors of this modulus of this public key? At some point, when you have a stable enough, large enough quantum computer, the answer you will receive will be a deterministic private key. You'll know that if this is my modulus, then, amongst the possible factors, this has to be the factor that, represents or corresponds to the private key. So instead, imagine that the public key is a set, not set. It's let's say a matrix of polynomials. And what we're doing now is we're taking something as a prime factor, and we're adding some noise, to it. So we're taking a few extra numbers and adding as noise to it. And these numbers are represented as a matrix of polynomials. So that formation, that type of problem is called the learning with errors. And this error portion of the problem is the noise that I'm referring to. And what that means is that the party that is responsible for decrypting, the party that knows the secret, is the only party that knows the secret. And what is the secret? Well, that's the noise. And that's not something that a quantum computer can deterministically derive from anything. So you've taken a set of problems or set of polynomials, and the solution of polynomials is yet another result matrix. And it's not possible for this quantum computer to know what that matrix is, what that value is. But where this argument falls apart to some extent is that we're dealing with an integer ring. We're dealing with integers as my noise. So while it cannot be deterministically derived, one may be able to guess it. So for a small enough problem, maybe that's okay. But for enterprise grade security, you're still dealing with numbers that could be guessed. So the next step, which I haven't shown here, but the next in between is the ring learning with errors, our LWE problem. And in that, what we do is instead of an integer ring, we have a polynomial ring. So now, we've basically increased the size of the matrix. Every element within that ring is a matrix. And I mean, maybe some of you know, maybe some don't, but your ring is defined with some operations, and one of the operations is a non-commutative multiplication. And the way you achieve that non-communicative multiplication is by performing that operation on a matrix. So, and these are in the abelian group. So they're square matrices, and that property, the very property of that ring is what makes those integers or the space that it will define is what makes it difficult to guess. But if you wanted it to be even more secure than that, so you take the ring problem and now you kind of try to make it more difficult to guess, is where the module learning with errors enters picture here. With MLWE, what we're effectively doing is that we're taking the ring which we had previously defined. So now you have all these matrices defined in that ring, and you have defined a distributive addition operation on it, and you've defined a non-commutative multiplication on the same ring. And the resulting or the result of that is then multiplied in a k-fold Cartesian system. And that result is what makes it, quantum safe or quantum resistant, because now you've introduced a noise, and the property of that noise is such that even if you're to kind of do quantum Fourier transform on that noise, you're not going to get interference pattern that will help you determine, whether these are relativistic or at least somewhat, closer to the original issue, and that's how you arrive at this ML solution from the NIST, or what was done through Kyber is through this mathematical property of the rings. So if you want to go to the next slide. Okay, so I covered some of this, so that's the definition of ML. That's your module lattice. You took a module, and on a lattice point, you've basically derived some noise and introduced that noise in your equation. So the next step, in this MLKEM, the next step, sorry, no, you can stay here. The next step in MLKEM is we have this algorithm now. We've done this quantum resistant crypto. We now need to, make it available for communication. So, that was maybe somewhat straightforward, because what we're doing in encapsulation is we're taking the standard group within TLS communication. So the group extension of the key share extension of the TLS protocol is where, we will utilize this MLKEM. And that's how, the quantum safe crypto became available to TLS communication. So we have a short demo, that shows where these algorithms live. And, we can also show you in a PCAP, like if two endpoints are talking, then where will that key share appear? So Nacha, I'll hand this over to you now. Okay, so what we have here, I'm seeing the XML firewall, and the front side for that firewall has a TLS server, and in that TLS server, in the advanced properties of the TLS server, you can define KEM algorithms. So if you want to show that, maybe the server profile itself.
So this is the front side. So it talks to the client with the classical algorithm at port 2050, and to the backend, it uses the client profile, which uses the MLKEM key share algorithm. So we can just go over that. So yeah, MLKEM is enabled only with the TLS v1.3. So we have that one, and in the advanced we have the various MLKEM algorithms listed. Yeah,
something I did not mention previously is that the NIST has standardized MLKEM, which we do support. But in addition to that, there are also some hybrid algorithms, which are combination of classical cryptography and hybrid. So, if you wanted, like, let's say that you're not completely sure that the mathematics of quantum safe crypto makes sense, or, maybe we don't know whether, how the NIST has exactly vetted that. And you wanted a solution that covers both, the known and mature classical crypto algorithms combined with your new MLKM algorithms, and that's where these hybrid algorithms can also be used.
So yeah, the other one is the backend with the TLS server profile, and this server profile again uses TLS v 1.3 with MLKM key share, and yeah, and this is just a small. The service just basically signs the XML input. So yeah, we have. So yeah, so that's what it basically does. Just input, and it gives back the signature, and the front end and back end communicate to each other with the MLKEM key share, and then we have this is a pre-recorded PCAP of this, and so we can see the front end communicating to the curl client with.
Yeah, so there are two hops here. In the first hop, the curl client, which is using classical crypto algorithms, communicates with the front end of that, the first hop of that service, the XML firewall service, and they talk to each other using classical crypto. And as you see that, the client advertised or the client, advertised these classical groups. That's one of the negotiated groups now would be, one of the classical algorithms. And in the next hop, the service then communicated with backend. The backend was listening using a server that defines quantum safe crypto, and the client also offered quantum safe algorithms. Notice that they appear here as unknown. That's because these groups are, they haven't been formalized. So we have the algorithms formalized, but the group identity is not formalized yet. And so Wireshark, shows them as unknown. And the server was able to communicate using one of these algorithms. There's 4132 under key share. Yeah. And so, the end result here, what you have here is that that key share was done using quantum safe crypto. And, that's how DataPower is utilizing quantum resistant algorithms. Okay. Thanks, Nacha. So that's what we had and we wanted to share with you. Ulash, anything in closing?
Yeah, no, this was very educational for me as well. So thank you for this, all of you. So yeah, there is really some deep mathematical and backgrounds for this. So what I'm kind of want to highlight is quantum safe. Okay, maybe it's not a problem for today, is right. That's my also conclusion summary, but definitely that's something we need to get ready from this day. And as DataPower, we are getting there. So we already take the step ahead forwards, and yeah, it's not just about when you talk about this quantum safe cryptography and all the background behind that. I can definitely say that, look, this is not just like a marketing bubble, right? So it is really something that might happen in the future, or maybe it's not that long term feature. So yeah, so that's. Yeah, that was a really good educational information for I believe many of you in the session. So thank you for this. But going forward, we will definitely continue to invest in this. So like any any security problems, because algorithms are today's algorithms might always fade, right? So you need to always keep up with that standards, keep up with the security threats. So that's I've been telling in all our sessions in TechCon at least. So now you heard it from the first hand from our experts that why it is important and how much work we are putting into this. So it's not just easy investments. So that's all I want to say to close. But anytime you can reach out to us. So if you have further questions. So yeah, Brian. Hopefully we are not over. Well, good, just on time.
Yep. No, we've got actually 5 minutes left. So anybody does have a quick question, please feel free to ask. If you don't want to get into it here, or it's a bigger question, please join our office hours, which will be at 2:30 p.m. Eastern. That's when we'll have our speakers there from the track for the day. And again, it's an open session. It's there for you to ask questions, to have a topic of discussion, whatever you want to talk about. So also, please notice the poll. It's actually the session survey, bottom left corner of your screen. Please take a moment before you leave. Answer those poll questions, help us get the feedback from you, on how we can improve. Every year we do this, lots of sessions every year, and we just want your feedback so we can continue to deliver what you want from us on this. So also, if you haven't heard, the IBM Tech Exchange Conference this year is in Orlando. So October 6th through 9th, join us there. Again,